So I want to tell you that everything that we've been doing so far that applies to water is also going to apply to all the other things that we're going to deal with in these tables here. So you're going to see tables here for water. You're going to see table for R22, which is refrigerant 22, R134A, ammonia, and for propane. Okay, everything that you're going to see here, the way I handle things, finding out what the saturation line is, if I'm above it or below it, that's going to be it, out for everything. But there's one important difference in that the H2O has it has a liquid table. Okay, it has a liquid table. R22, R134A, ammonia, and propane, they have saturation tables. They have superheated vapor tables, but there's no liquid table here. This has no liquid table. So what do we do if you don't have a liquid table? How do we go and find the property if we find that the state is a liquid? Well, we do something called the liquid approximation. The liquid approximation states that the specific volume or the internal energy or whatever we're dealing with that we're looking at of a liquid is approximately equal to the specific volume of the saturated liquid at the temperature that we have been given. Okay, the specific volume or the internal energy of the saturated liquid at the temperature that we've been given. It's important here that we're talking about the temperature. Okay, the temperature. We're going to say, hey, the properties don't change very much from a saturated state to those of the liquid state that you're looking at. They're so darn close that we're just going to approximate them as a saturated state. And in fact, as we go down here, let's look at table A5. Table A5, you can see that for water, the liquid table starts at 25 bar. 25 bar is going to be 25 times atmospheric pressure. So what happens if you're just at 2 bar and you have a liquid, or at 3 bar if you have a liquid? Well, you're also going to use a liquid approximation up here for liquid water when you are in that lower pressure range. Only when you get to the higher pressure compressed waters do we say that now the properties of specific volume, internal energy, those are going to be much greater, or they're going to be much different than in the saturated liquid properties at the temperature that you've been given, and so that you can go and look them up in an actual table. But the liquid approximation is going to be one of your primary tools for finding the properties for liquids. Okay, next thing I want to talk to you about. Let's go here and let's pretend like we have water again. And we are saying that now the temperature is going to be equal to 220 degrees Celsius and the pressure is equal to 1.4 megapascals. Okay, so we're going to go through here and we're going to do the same things we've been doing so far. We want to figure out if it's a liquid, if that's a vapor, or if that's a liquid-vapor mixture. Liquid vapor mixture. And I am just going to use my old friend, a TV diagram in this case. Now I think I'm getting pretty comfortable with this. I'm going to use a TV diagram, not worry about a PV diagram. Although the PV diagram is always there to help me out, I'm going to just use a TV diagram. That's what my go-to diagram is for when I do problems. That's a curvy line, but you know, my diagrams are just beautiful for you. You're thinking, man, who could make better diagrams than Dr. Wanklin? 1.4 megapascals, which is equal to 14 bars. Okay, and I want to see where I saturate here. Okay, let's go to our pressure table, which is going to be table A3. Table A3, as we get to it, table A3, we're looking for 14 bar, 14 bar, 14 bar. Darn it, we have 10 bar and we have 15 bars. We don't have that number, 14 bars. And so what we could do here is we could interpolate, or we could go and say, maybe this, I don't want to use this one. I'm going to use my temperature table or my PV diagram to help us out here. And you know what PV diagram is going to tell us exactly what it is. I'm going to show you that in just a second. But let's just pretend like we couldn't use the PV diagram. Look what's happening here. We know that this is going to, that at 10 bars, we saturate at 179.9. And at 15 bars, we saturate at 198.3. So we could say that approximately we're going to saturate here at maybe we're going to say 192 degrees Fahrenheit. Okay? And we're above that. We're above that number. So we're at 212 here. So we are going to be a superheated vapor. Okay? We're using good engineering judgment to go through here with this. Let's just confirm that. If we were a little bit worried about that to see if we were right or not, let's confirm that with our PV diagram. Here's our PV diagram. It's going to have a line of constant temperature, and that line of constant temperature is at 220 degrees Celsius. Okay, 220 degrees Celsius. We go up here to 220 degrees Celsius, which is in this. 220 degrees Celsius tells us we saturate at 23.18. 23.18 bar. We're at 1.4 bar. Okay, we're down here. So, sorry, we're not 1.4 bar. We're at 14 bar. 14 bar, which is right here, which intersects over here. Still telling us that we are a superheated vapor. So we've confirmed that both times. We're good to go. We're ready to move on here. What I want to do is I want to find out what the specific volume is for this. Okay, so we go down here and we say, oh great, we are now a superheated vapor, la da 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 da, superheated vapor. Well, we now had to find superheated vapor for 14 bars, and I'm like, oh man, look here, I don't have it. I don't have 14 bars. I have 10 bars and I have 15 bars. Okay, so I'm going to have to interpolate. At 220 degrees Celsius. And I look here and I say, well, and I also don't have 220 degrees Celsius in my table. This is something called double interpolation. Double interpolation. Now, the thing about double interpolation is you actually have to interpolate 3 times. It's kind of a bad, it's interpolating, you're interpolating one way and then the other way. That's what they call double interpolation. But you actually have to do 3 different interpolations to get this to work. What I like to do when I have double interpolation problems is I like to make myself another little graph here, another little table here. So I'm going to say that this is going to be 10 bar, and then I'm going to do 14 bar, and I'm going to do 15 bar, and then I'm going to have, in my table, I have a 200 degrees Celsius. I'm looking for 220 degrees Celsius, and then I have to do here 240 degrees Celsius. And then I put in what the tables give to me. Well, they give me 200 and 10 bar. So 210 bar is going to give me a specific volume here, and I'll use a different color. Let's make sure it's easier to see. 210 bar is going to give me 0.2060. 215 is going to give me 0.1325. Okay, 240, 0.2275. And 240 here is going to give me 0.1483. Okay, 0.1483. So what I'm trying to find is actually this box right here in the middle. So there's 2 ways to do this. The first way is I could interpolate between these 2 numbers to get this number, and these 2 numbers to get this number, and then interpolate between these 2 numbers to get my value that I'm looking for. That's one way to do it. Or, if I didn't want to do it that way, I could interpolate between these 2 numbers to get this number, and interpolate between these 2 numbers to get this number, and then interpolate between these 2 numbers to get this number here. That's the second way to do it. Both ways are completely acceptable. However, there's a way in this particular problem that I think is the best way to do it. And that is because in this situation, we happen to have that special interpolation situation where our value, 220, is halfway between two values. And when your interpolation value is halfway between, that's just a simple average that you can do here. So I'm going to pull out my calculator, and I'm going to find out what these values are here. So I'm going to put 0.2060 plus 0.2275, divide that by 2, and get 0.21675. And then that makes sense, it's between those two numbers. Then I have here 0.1325 plus 0.1483 divided by 2, 0.1404. Okay, that's the easy. I don't have to worry about any lines or anything else that I have to work with. Okay, but now what I have to do is I have to find out what this value is here. Okay, and that's going to be your lecture question here. I want you to find out what that value is. Again, it should be between these two numbers. It should skew towards the 15 side, and put it into our the quiz question. Okay, that will be where we'll end this segment of the video.